All right. Hi everyone. Thanks so much for coming to this workshop, and thanks so much, Brent, for putting all this together. So I'll be moderating and checking the chat for questions. So Brent doesn't have to do that while he's also presenting. Yeah. So I think without any further ado, we can just get started. Unless you have anything else you want to add, Brent.
I just want to say that I'm sure some of you may have questions about how to install either Pyomo or Gurobi Py or any one of the many solvers that Pyomo supports. And I just ask that if you do have those questions, you delay them until the Q&A at the end of this meeting. With that said, what is this tutorial? This is a tutorial, an introduction to math modeling in Python. We're going to be primarily looking at the Pyomo and Gurobi Py packages today. So let's jump right in. What is Pyomo? It's an acronym for, as we see here, Python Optimization Modeling Objects. It is a framework implemented in Python for defining optimization models. And to be very clear, Pyomo is a framework and it is not itself a solver. It is compatible with many open source and commercial solvers, but it is itself not a solver. This piece of software is developed at Sandia National Laboratories, and I don't know, it's been around for nearly a decade, I think, and it's part of the Coin OR project, which is a bunch of libraries and solvers for I think it stands for computational infrastructure in OR. So the pros and cons. Now, if you've never used a modeling language before, you know, this may this may all sound very arbitrary, but if not, what are the pros? It's free as in beer. You know, this is Richard Stallman lingo here. Free as in beer, it costs nothing. And it doesn't matter if you're an academic or a professional. It's free as in freedom, which has to do with the licensing. This is licensed under the very loose 3-clause BSD license, or the modified BSD license. It's cross-platform, so you can develop this on Windows, Mac, and Linux. As I mentioned, it supports a wide array of open source and commercial solvers. And additionally, it supports both declarative and imperative or functional programming paradigms. Now, some cons. At least, you know, you can compare this with Gurobi Py, which we'll see in just a moment. It does not have any built-in support for matrix and vector operations. So if you're going to do something like AX equals B sort of constraint, you can't just create a matrix A, a vector X, and a vector B, and then say, implement that constraint just using those constructs. You have to do sums and iterate over indices and things like that. So that's what I mean by this no built-in support. It has, I think most modeling languages, clunky handling of jagged sets. So if you have a set of indices and then you need to define additional sets that are indexed in that original set, that gets to be a little clunky, implementing that in Pyomo. There are some scalability issues. The main, right here on the left, we said a big reason to use Pyomo is that it supports many solvers. The downside of that is that it's built to support many solvers. It's built to be general, and that affects the size of models you can build in Pyomo, or at least the performance at scale. For small models, you'll never notice this. And then it has also, because it's supporting many solvers at a general level, it has limited support for the specific options you can pass to each solver. And compared to most other modeling languages, I would say that Pyomo is very programming centric versus modeling centric. I put that in the con category because we're all in OR here, but I think if you're of a more computer science mindset or a software engineering mindset, you might want to actually put this in the pros column. So if we're going to develop a model in Pyomo, you have to attach, you have to set up the sets and parameters and constraints and all of that, all of these things listed here. In Pyomo, all of these things get attached to the model object itself. And I'm going to put an asterisk next to that. There is an exception with sets and parameters. You don't technically have to attach those to the model, but I generally think it's best practice to do so. So that's why those are shaded in the light gray here. And everything else is shaded in dark gray because it's actually required that the variables, constraints, and objective function are attached to the model. The arrows here are simply signifying the order in which you have to define these constructs. If you have a parameter that's indexed in a set, you cannot build it in Pyomo until you have defined the set. Similarly for variables. And then if you're going to build constraints, obviously you need the parameters and variables that comprise the constraints and the objective. So this is just giving you an idea of what order should you build the model in. Sets first, then parameters and variables, then constraints and objective function. Now let's move on to Gurobi Py. Gurobi, you might think, that's a strange name. It's actually, the acronym is the first two letters of the three people that founded Gurobi. And just a brief history here, all three of these people, Gu, Rothberg, and Bixby, formerly worked at Cplex and then split some years ago to form Gurobi. Much like Pyomo, Gurobi Py is, whoops, looks like I got a redundant bullet here. It is a framework for defining optimization models. Gurobi Py is not a solver. Gurobi is a solver. Gurobi Py is the Python interface for accessing the Gurobi solver. And Pyomo, you can just get on any of, PyPy or from the Conda repositories. Gurobi Py ships with the Gurobi solver. So if you want to install it, you need to acquire the solver package first. Now let's move on to pros and cons of Gurobi. Also free as in beer if you're an academic. So it's no cost for you to use if you have an authenticated academic email address. With Gurobi Py, you have complete control over all of Gurobi's solver options. Gurobi Py, unlike Pyomo, has at least limited support for matrix vector operations. I think the limitation there is that if you're going to do like AX equals B or something like that, it's just that the variable construct has to be one-dimensional. You cannot use the same features for two-dimensional variable constructs like matrices. Also, like Pyomo, since it's implemented in Python and Gurobi solver itself works on Windows, Mac, and Linux. Gurobi Py also works on Windows, Mac, and Linux. And at least relative to Pyomo, it's much more modeling centric in its approach. Now, cons: it is not free as in freedom. It is licensed under the Gurobi proprietary license. Not necessarily an issue, but just something to note. Of course, if you're using Gurobi Py, the only solver available through Gurobi Py, as far as I know, is Gurobi. And Gurobi is limited to solving LPs, QPs, and QCPs, and also the mixed integer variants of those problems. And another con, I think of this as a con, again, depending on whether you like to program more from a software engineering point of view or an OR point of view, this last bullet you could arguably put in the pros column. Sets and parameters in Gurobi Py, you don't have to link them to the model. And the reason that might be an issue is that if you need to integrate the optimization model in a larger framework, you can have scoping issues. For example, if you need to pass the parameters to a function to set up some expression or some constraint, then you need to be explicitly thinking about, oh, I need to pass the set of C parameters or the set of A parameters. Whereas in Pyomo, you have the model and you attach everything to the model. So in anywhere in a program, if the model is in the scope, everything attached to the model is also in the scope.
Hey, Brent,
And
I had a quick question.
yes.
So about the solver options, I was curious, like what kind of solver options are there? I haven't really ever worked with what options you're handing to the solver. So is this something that you yourself use at all? And is this like a real limitation of Pyomo that you can't really send options to your solver, or is this something that you don't really run into that often?
So just to be sure, Pyomo does support sending options to the solvers. It's just there's a limited set of support because it's trying to support everything. It's trying to support many solvers, but it's only supporting some subset of all the features that each of the solvers supports. Now in Gurobi, there are an enormous number of solver parameters or hyperparameters, I guess you could call them, that you can define. Some of them are related to termination criteria. So that would be like in a mixed integer program, you might have the MIP gap, which you could define to be relative or absolute. You can define objective value thresholds for termination or time limits, or just say stop when we get a feasible solution. There are also options to specify how you want to do branching in a branch and bound scheme, which variables to prioritize. And then there's a whole other set of options just for defining how aggressively you want to try to add cuts, whether it's MIR cuts or covers. I don't know, there's probably 15 or so different types of cuts that Gurobi will try to add on the fly. And for each one of those, you can say, don't add any, add some, or try to add those cuts very aggressively. Did you have something specific in mind?
I was just kind of curious, like how big that difference is between Gurobi and Pyomo. Pyomo does support some solver options. Like, how limiting is it that you can't necessarily give it all of the ones that you might want?
I think that
because I imagine like MIP gap probably is something that you would want to be able to pass to like all of your solvers, or
I think everything I just mentioned is supported, at least in Gurobi. Pyomo has support for all of those options. I think in general, Pyomo has very good support for all of the Gurobi solver options, but that is not generally true for all solvers and all options. Yeah.
I see.
So let's just recall, this was what our dependencies looked like for building a Pyomo model. Now let's compare that with Gurobi Py. In Pyomo, I said you can optionally attach the sets and parameters to your model, and I recommend that you do. In Gurobi Py, that functionality does not even exist. It's not possible to attach the sets and parameters to your model, but you must attach the variables, constraints, and objective. So that said, your parameters might just be a normal Python dictionary or a Pandas data frame. And your sets might be a Python set or a Python list or the index of a Pandas data frame. It doesn't really matter what it is. Just note that it is not actually attached to the model in Gurobi Py. So that's a lot of blah, blah, blah on slides. I'm sure what most of you are really interested in is seeing the code. How do I do this? Well, we can move on to that. Let me drag that window over. Okay. The first example I'd like to look at here, and let me zoom in just a hair. The first example I'd like to look at is a specific instance of the binary knapsack problem. So I think if you've all taken LP, you're familiar with the linear knapsack. Here we're saying binary knapsack. The decision variables are all restricted to 0 or 1 values. That's the only difference. So it's just a discrete version of knapsack. The first thing we need to do is import Pyomo environ or environment and Pyomo opt. Now, when we construct the model, mostly we're using things exclusively, I think, we're using things from the environment package, which I load as PE. And then when it comes time to solve, we're loading things from Pyomo opt, which I import as PO. And so I'm defining the solver up front, even though I don't need it for another couple code blocks. But here I'm going to use the solver glpk, which I have already installed on my system. So this is the model. You can see I have the objective function there. There is the single knapsack constraint, and all of the variables, as I mentioned, are binary. Now, how might we implement this? Well, if we have a specific instance, first let's create the model. Here we call that, we construct the model using a concrete model from Pyomo environment. And then in this next code block, we're attaching variables sequentially. In this problem, there are 5 variables. Here we have 5 lines of code to create the 5 variables separately. We can see that we're constructing these from the var construct from Pyomo environment, and we are restricting the variables to the binary domain. Now, if this were a linear program, you might instead specify reals or non-negative reals. There are also integers and non-negative integers. I think there might even be a few more types for semi-continuous variables, but I don't quite recall at the moment. Anyway, we've defined 5 variables here, binary. The next step, let's implement the objective. So we have 3 times x1, 4 times x2, so on and so forth. We just have this expression that we've made using integers, normal Python constants, and Pyomo variables. So this line here, this constitutes an expression. Now we create the objective and attach it to the model by setting up an objective construct from Pyomo environment. There are 2 important things here we need to do. First, we need to set the sense of optimization. By default, Pyomo wants to minimize, but here we need to maximize. So I'm explicitly specifying that. If it were minimization, I would not need to specify this, but I might want to do so anyway, just to be explicit. And then second, we need to define what is the objective. There are a number of ways to do this, but at least in this example, we're going to do it using the expression keyword, and we're going to pass it this expression that we just created in the previous line. So let's execute that. Now we have our objective in place. Now let's scroll back up. Now we need to implement the constraint. Well, this is very similar. We have the left-hand side here, which is constructed in exactly the same way we constructed the objective. And then we're also tacking on a less than or equal to the right-hand side, 20. So I guess technically this isn't an expression. It's kind of a misnomer here. It's two expressions that are related by a Boolean operator less than or equal to. It's important to note that if this were an exact equality constraint, it would not suffice to have one equal sign here. That's not a Boolean operator in Python. That's an assignment. You actually need two equal signs, just like if you were doing a comparison. But here we're going to do less than or equal to, just as we specified. We attach, in much the same way, we attach a constraint to the model using the constraint construct from Pyomo environment, and we pass it the expression, which is really a relation of two expressions. Now we're ready to solve. We have everything in place, our variables, our objective, our constraint. We previously defined the solver. That was in our second line of code. So we just say solver, invoke the solve method of the solver, and pass the model we just constructed. Here, actually, I forgot. If you want to see the solver log, you can also say T. And this is a T. Even though we're spelling it TEE here, you can think of it as like a T, like in plumbing, where whatever gets printed to the log file, we're also teeing into the standard output here in our notebook. So we're going to see the log as it's written in real time. So here is the GLPK log. Indeed, we found an optimal LP solution in the relaxation version. It did its branch and bound stuff or whatever it needed to do, and then found an integer optimal solution. Fantastic. So we have the solution, great. What is it? To access the values of the variables after you've solved the problem, you use the value function from Pyomo environment. At least that there are multiple ways to access the values. I find that this is the most consistent way of doing it. So let's run this, and what do we see? X1 has a value of 1, X2 has a value of 0, and then X3, X4, and X5 are all also 1. So we're saying put everything in the knapsack except for the second item. And collectively, here we're also applying PE value to the objective and finding that the total value of the items we put in the knapsack is 25. And that was it. However, this is a really terrible way to implement Pyomo models in general because it's completely fitted to the specific instance we just considered. Generally, in Pyomo and virtually every modeling language I've ever used or seen, it's much better to define the model abstractly or generally, and then plug in the parameters as you need. So what's the general form of this model? Well, it's maximize a linear combination of the xi's subject to a different linear combination of the xi's less than or equal to the size of the knapsack, b, and then just however many variables you might have, those all have to be in the set 0 or 1. Yes, and I say it here, we're assuming the set of items is n of some arbitrarily sized set. So unlike we did before, you noticed up here, we never defined sets or parameters. That's because we hard coded them into the problem. But now we're going to revisit that. Let's recreate the model. And now let's say, I need to create the index set n. One way to do that is using a range set. There's no reason that your indices have to be integers. They could be strings or any immutable object in Python can be used as an index in Pyomo. So here we're saying a range set from 1 to 5. What does that look like? Well, it's the integers from 1 through 5. And note that this is a little different from Python's built-in range. If we do range from 1 to 5 and convert that into a list, that actually only gives us the integers from 1 through 4. So this is a little different from Python's built-in range. Now we need to define our data, the parameters of our problem. Since C and A are both indexed in the set N, we want to define these using dictionaries where the keys are the items from the set, the elements of the set, and the values are the actual value of C at that index. So here we're saying C index 1 is equal to 3, which if we go way back up to here is exactly the first coefficient of the objective. And we repeat that for the rest of the indices, and then again for A, which are the constraint coefficients. And then we define the right-hand side of the constraint, B equals 20. Now we've just defined these as normal Python data structures. However, we need to attach these to the model. So let's say model.c equals a param. We did not use this before. A param that's indexed in N, and we want to initialize it using C. Now, much like the constraints and the objective, there are many ways to create the parameter. Before we used, for the constraints, we used the expr or expression keyword. Here we're going to use the initialize keyword. We could also pass a rule which operates on a function, but here let's just pass it a static dictionary. Similarly for A is also indexed in the set N, and so we're going to pass it a dictionary A. And then B, it's just a constant. It is not indexed in N, it's just a single value, so we just initialize it as the constant B. Now, if we want to print these things, we might say, well, let's print model.c, and it should give us the values. But that's not actually how Pyomo works. Oh no. Oh, I didn't run these code blocks. So if you print model.c, you just get the name of the object, which is a little unintuitive, but that's how Pyomo returns it. If you want to access a value of C, you actually have to index it. So here we see model.c index 2 is 4. And worse yet, this is inconsistent, because if you want to access a parameter that's not indexed, how do you do that? You just said, if you want to get the value, pass the index. Well, what if it's not indexed? Then you have to attach dot value, or you could similarly use, I believe, PE value as we did before. Yes. So either one of these two ways will get you the actual value of that parameter. Now, before, we created 5 separate variables for the specific instance, but now we're considering a problem of generic size. So we know that X must be indexed, again, in the set N. That's what we pass here. And we, again, want to make it all of those variables binary. So now we've just created an X that you can also access via indices. And so this time, instead of explicitly saying C1 times X1 plus C2 times X2 plus, all of those terms, let's just say in general, we want to take the sum for all I in N of C sub I times X sub I. Right? This is just the objective function. And we can define it using the sum function, which is from Python. This isn't even from Pyomo. And then we just create an expression using the objects we already attached to the model. And this second line of code, this is copy paste from above. We created the expression. Let's just create an objective from it now. Similarly, for the constraint, I'm creating the left-hand side using a sum in just the same way. And the right-hand side, I'm just defining as the parameter b. And as the expression, I'm saying, let's let the constraint be that left-hand side less than or equal to the right-hand side. So let me run these two code blocks. And again, we solve it in exactly the same way. Solver.solve, pass the model. And we are able to access the variables in the same way. And we can see that the solution is the same because the parameters we used in the general instance were the same as from the specific instance above. So these are kind of like, this is a very bare bones model in Pyomo. And I'll take a moment here in case anyone has questions about anything from this script.
Yeah, I have a quick question. So what if we have a lot of variables, like from x1 to x20 or 30? So from the current script, I think we are typing our parameters into the program, but if there is any like easier way to do that here.
You're talking about like these things here?
Yeah.
So this is just an example. I think in most cases, if you're solving a large LP or IP or any kind of model, I suppose, you're not going to want to do that by hand. And you probably already have that data in a database or in a CSV file or some other standard type data file. I think what's important is that as long as you're able to import that data into Python and then format it in a way that Pyomo accepts, you shouldn't have any issues there. And I do have an example in this repository where I load parameters from file. I believe it's from, I actually don't remember. It's either a CSV or a YAML file, but that's, I believe, this fifth example script here. So I'll just open this up briefly. Here I'm opening the file, I'm loading parameters. Similarly for edges, this is a problem on a graph. And I'm converting those into dictionaries that I then pass in the same way I pass the dictionaries here using initialize. So as long as you can get the data, I guess, into a dictionary format, there's no difference in how you specify or attach those numbers to Pyomo. It just may require a little bit more work in pre-processing. Did I answer the question or am I misguided here?
Yeah, thank you so much.
So I'm going to move on to a second example. This is a linear program exercise that I pulled from Dr. Bard's book. I'll just briefly read the problem statement. 10 jobs are to be completed by 3 workers during the next week. Each worker has a 40-hour work week, so that's an upper limit. The times for the workers to complete the jobs are shown in the table. The values in the cells assume that each job is completed by a single worker. However, jobs can be shared, with completion times being determined proportionally if there should be a period there. If no entry exists in a particular cell, it means that the corresponding job cannot be performed by the corresponding worker. Set up and solve the LP. Okay, so here we have workers and tasks. What we require is that every task is completed and that none of the workers work more than 40 hours. The objective is to minimize the total time. So this is worker hours required to complete all of the jobs. So what do we have here? Right away, we know we have a set of workers, we have a set of tasks. We're going to have a set of parameters that are indexed in both the workers and the tasks. And we have at least 2 sets of constraints, and maybe more depending on how we define the variables. So here, let's import import Pandas, import Pyomo environment and Pyomo opt. Here, I've just said, this is the set of workers, this is the set of tasks. These are my parameters. You can see here, I've defined the parameters C as a dictionary where the keys are actually a tuple. So the first element of the tuple is the worker, and the second element of the tuple is the task, because the parameters are indexed in 2 different sets. So the way you do that is to use tuples. And then the value, it takes worker A 7 hours to complete task 2. And the max number of hours anyone can work is 40. So first step, define the general framework for this problem. What is the general formulation? Well, it's to minimize the sum over workers and tasks, the product of the time it takes for a worker to complete a task times X, which here we define as the proportion of task T that worker W completes. And this is the total number of hours that everyone collectively works in the week. Now, subject to, for every worker, the total number of hours the worker works over the week has to be less than or equal to H, which we define as 40 here. And for each task, we're saying that the sum of the proportions that each worker completes must be equal to 1. The task must be completed. And then finally, the proportions intuitively must all fall between the value of values of 0 and 1. So we just place an upper bound, right? We're saying X is non-negative, and they're all upper bounded by 1. So this is the model we're going to implement in Pyomo. So again, first step, create the model. Second step, if we go back to our little picture here, we have to define the sets first. So we have the set of workers, which we initialize with our worker set, tasks. I don't know why I put this here. So those are the sets. And then we have 2 parameters. We have C, which is indexed in both the set of workers and the set of tasks. So however many index sets the parameter is indexed in, you pass those one after another here. It could be 20, it doesn't matter. Those are always the first arguments to be specified. And then we're saying initialize those to be using the dictionary we already defined. And in case there is an element in this dictionary that's not defined, right? So for example, there's no element here for worker A task 1 because that's not possible. Just to keep it simple here and use square index sets, we're going to say, okay, it's possible, but it costs a lot. So let's give that a cost of 1,000. It takes 1,000 hours to do that. Just make it large enough that it's never optimal to pick that option. And then
I think
max
Ella has
hours.
a question.
Oh,
Sorry.
Go right ahead.
Real quick, I was just wondering if the order you put the index sets, so like the model.workers, model.tasks, does that matter if you get them in a certain order or not? Or as long as you have them down, it's okay?
That's a fantastic question. So let's just start with, why did I put them in the order I did here? The reason is that when I defined this data, I put the order as worker first and then task. So the key is worker task pairs. I could have made them task worker pairs, and then I'd have to flip the order here. Because when we initialize, basically what happens, behind the scenes is Pyomo is looking for every combination of workers and tasks in C. If it doesn't exist, it's going to complain. So if I flip these here, it's not going to find any of those. So the order does matter. And then as long as you're consistent, you can make it any order you want. But because of how I define my data, I had to do it this way. Okay. So here I've defined my parameters. Similarly, we have the variables X also indexed in the workers and the tasks. These are real valued. I could have made it non-negative reals, but I don't need to because I'm also going to specify bounds. So instead of just defining these on the non-negative reals and then later adding a constraint that says none of these can be larger than 1, I'm just going to do that here because the functionality exists in defining the variables. Say they all must exist in the range in the interval 0, 1.
So I have a question.
Yep.
So in the fifth step where you were doing parameters, how come you don't have to say pe.param for max hours?
So in fact, I probably should. I don't necessarily need to. Oh, right. Initialize. The reason that I can get away without doing it is because it's not an indexed parameter. But definitely the indexed parameters, if you're going to construct them this way, you have to do it through pe.param. Yes.
I see. And so functionally, you wouldn't use it any differently if you don't initialize it as a parameter. It would still like syntactically be the same from here on out.
That's correct. Yes.
Okay.
But it's good. I mean, that's a good point. We should keep it consistent. Where did I leave off? Need to redefine X. And in just the same way we did before, we create an expression, the sum of C times X for all workers and all tasks. We attach that to the objective. I'm just repeating myself now. We've seen this. What we did not see before is to have a list or set of constraints, because in the knapsack problem, we only had one constraint. Here we have several. In fact, we have a set of constraints indexed in the workers and another set indexed in the tasks. So let's first deal with the constraints that are indexed in the tasks. We create a placeholder or an empty set of constraints that we populate. So tasks done, this is a set of constraints that is constructed from the constraint list object from Pyomo environment. And then we iterate over the tasks and add constraints to that list on the fly. So this is just saying every task has to be completed. Left-hand side, double equals. Again, remember, we can't get away with one equal sign because that's an assignment. This is a comparison. We need this condition to be true. And then we also have the constraint that none of the workers can work more than 40 hours. So we create another set of constraints called hour limit in the same way. Iterate over the workers, require that the sum of hours worked for each worker over the tasks is less than or equal to max hours. Oh, and I forgot to mention here, we have model.hourLimit, which is the same as what we have in this line. And then we're just saying add a constraint using .add method. And that's it, right? We just had this model to implement, objective function, 2 sets of constraints, and the variable bounds. I'm going to solve this again using GLPK. We're going to see the log because I set t equal true. And now this time, again, right, for Pyomo, the beauty of using Pyomo and the beauty of using Gurobi Py is that they're written in Python. And if you're going to write a Python script, then you can use any Python library you want, right? You can take advantage of all these other beautiful libraries we have for dealing with data, whether it's Pandas, NumPy, Matplotlib, you know, anything you want for processing data. Here, I don't want to get into the details of how I'm doing this. If you're not super comfortable using Pandas, you know, maybe you want to look through these last 4 lines of code on your own. But essentially, I'm putting all of the solution data and parameter data into a data frame just to, and then I'm going to do some operations to check you know, what is my solution? And so here I have a table where the rows are the workers and the tasks are the columns, and the values in the table are how many hours each worker spends on each task. And then I can do operations, you know, sum across the columns to see that indeed none of the workers are working more than 40 hours, and sum across the rows to see that indeed each of the tasks is completed according to the solution we obtained from the solver. Right, so that you know, there are easier ways of checking this where you just write a for loop or something like that. The only reason I'm including Pandas here is just to highlight, because you wrote it in Python, you can import Pandas and use that in conjunction with Pyomo. So I'm going to move on to the Gurobi Py implementation. Same exact problem we just saw, so I'm going to kind of speed through this here. Instead of importing Pyomo, we're importing Gurobi Py. One difference here in the data is that instead of using a normal dictionary, I'm using a default dictionary. And this is because the way that Pyomo handles default values is slightly different from Gurobi Py. So I'm just deferring, you know, the default value of 1,000 to the input parameter itself. So if we want to get the key a, 1 out of this dictionary, it doesn't exist in these values, so the dictionary itself will return 1,000. Same model, mostly the same process. So we also in Gurobi Py have to define a model object, which we do is gurobipy.model. We do not have to attach the sets or the parameters to the model. So we just don't have those lines of code here. That does not, you know, there's no equivalent from Pyomo. When we create the variables, we're using a function of the model to create the variables, which is a little bit different from before. If you recall, we used a constructor from Pyomo environment. Here, we actually have to use the model to create the variables. And we're saying, much like before, the variables are indexed in both the workers and the tasks. The variable type here I specify as C, C standing for continuous as opposed to discrete or binary. They all have a lower bound of 0 and an upper bound of 1. And I actually don't need the model.update here. So we define the variables. And I recommend that if you're going to look at this, you pull up one, you know, the Pyomo version of this on half your screen and the Gurobi Py version on the other half to see just how similar these two are. I'm of the opinion that, you learn one modeling language, great. You learn a second, you start to realize that it's really not different from the first in terms of paradigms. The code looks different, the paradigm is the same. Right, so move on to the objective, same paradigm. Create the expression, and then define the objective. You have to define, again, the sense of optimization. Here, just slightly different. We're defining it using Gurobi objects, and the expression is just a Gurobi expression instead of a Pyomo expression. And then again, we don't have to define containers for our constraints. We can just attach them to the model on the fly. So here, iterate over the tasks again, create the left-hand side, right-hand side, model.add constraint. Very simple, very straightforward. Similarly, for the other set of constraints, the process is the same. For good measure, we run model.update. And honestly, I'm not as well versed in Gurobi Py as I am in Pyomo. I don't have a firm understanding of what this does other than it's good practice. Yeah, if someone else knows how this works better than I do, feel free to speak up. Otherwise, I'll keep moving. All right, so let's just chalk it up to, we do that because it's good practice. Instead of running solver.solve, because Gurobi Py, right, you don't have any solver options. Sorry, you don't have any choice in solver. If you're using Gurobi Py, you're solving the model using Gurobi. So you can just run model.optimize, and by default, it's using the Gurobi optimizer, the Gurobi solver, to solve the model. And also we see here that the default behavior is to print the log when you run that command. Solved in 10 iterations in virtually no time at all. Optimal objective 8.8 times 10, so 88 hours, which is what we saw before. And in much the same way, I'm just using almost exactly the same lines of code, putting the solution and the parameters into tables to verify that the solution is indeed feasible. So we get the same schedule here. The workers are all working the same number of hours and all the tasks are again completed. So most of the things you can do with Pyomo in terms of inputs and outputs are the same things you can do in Gurobi Py. And again, I recommend that you pull these two scripts up side by side to see exactly how similar these two scripts are. And I know we are approaching the end of the hour, and there is one more example I could show, and we would definitely run over, or I could stop and take any and all questions you might have. I'm free to go past the hour, so I guess fire away.
I guess maybe what makes sense is, oh, Connor looks like he has a question.
Go ahead, Connor.
Yeah, I wanted to know, like, if there's like a paradigm to, like, if I had to like have a constraint that was like over all subsets of an index set, is there like a nice way to do that, or do I need to like enumerate all of the different like subsets using like iter tools or something?
Yeah. Are you thinking in terms of you need to define a constraint or a parameter? So yeah. So this would be something like for like traveling salesman kind of problem, for example, where there are an exponential number of constraints. Yeah, I would create a constraint list for that, and then use somewhere in the iter tools documentation, they say this is how you should define power set,
Mm-hmm.
and then iterate over all the sets in the power set of your indices.
Okay. Yeah, that makes sense. I was wondering if there's like Pyomo had like a way to do this that was easy, but that makes sense too, like that.
I think Pyomo does not have a great way to do that easily. I see that Ella has a question. Go ahead.
Yeah, this may be obvious to everybody else, but where would I be writing this script?
So I'm a fan of Jupyter notebooks because you can visualize everything on the fly and they're interactive. But I could similarly download this as a Python script. Right, and just run this on its own. Right, this is just the Python script equivalent of the notebook. I could just run this, and as long as in the notebook, I don't have to write print for these things to display, but you could just add some print statements to anything you want to see, and then run this script from a command line or in the Python terminal or from a Python, what's the word I'm looking for here? Something like Spider or.
Do you have Python? Whoever asked the question.
Ella?
Oh, yeah, I do.
Like Anaconda? And like the.
I don't know. I don't know a lot about computers, and I downloaded it this morning. So.
That's the kind of thing where if you're not familiar with Python, you kind of got to get into the weeds a little bit.
Yeah.
And that might take me a few minutes here. I'd be more than happy to walk through that with you sometime in the future.
Okay.
Okay, I see. Unfortunately, I can't see who raised their hands, but
I think Helen had her hand up first.
okay, go ahead.
Yeah, so I have a general question. So I'm currently doing a project which contains the continuous variable and also the binary variable as the indicator. And I'm also using Mac as the system. So which one will you recommend me to download, like Pyomo or Gurobi Py?
So I didn't really state this explicitly before, but here's where I really feel Pyomo is superior. Right, here's an example scenario. You have on your system the GLPK solver. All right, scrap that. You have the Gurobi solver. So you could write it in Gurobi Py, and you would have no issues. If it's just you, if you're the only one that needs to run it, you could implement it in Gurobi Py, it would be fine. But suppose you have collaborators that don't have access to the Gurobi license, then you're kind of, you're making it very difficult, if not impossible, for them to run your code because they can't execute the Gurobi solver. But if you wrote it in Pyomo, you can solve the problem using the Gurobi solver through Pyomo. And then if they have a different open source solver like GLPK, they can use the exact same code and just change the one line. They can just change this one line here to be GLPK, and on your system, it will be Gurobi. So I think if you're trying to do shared work with people who have different accesses to commercial and open source solvers, my recommendation is Pyomo. If everyone in your work group has access to Gurobi, there's no reason you couldn't or even shouldn't use Gurobi Py.
Thank you.
And to speak to your point about the types of variables you have in your operating system, there are no limitations there. you could use either.
Yeah, thank you.
And I know someone else had their hand raised. I did not see who, but you can ask your question.
Yeah, so if you're currently using Ample, when do you recommend like switching to Pyomo or Gurobi Py? Is there like a scale of problems or like a type of problems where using these is like better than using Ample?
So I'm not super familiar with Ample, but my understanding is that if you write a model in Ample, there are also several solvers that support that kind of interface or that kind of input. And in that sense, as far as I understand, it's very similar to Pyomo. I think you might only want to switch if there's a strong motivation to integrate your work within a larger Python application. I don't know that it would be super worthwhile to redo all of your work, just for the sake of it being in Pyomo or Gurobi Py.
Yeah. Thank you.
Mm-hmm.
I had a question. So here you have the PE.constraint list, and then you iteratively add those constraints to that constraint list. Other examples I've seen use like the rule, like you create a function, and then you, when you create your constraint, you just give it that function as the rule. Is there like a difference between the two? Obviously, you seem to prefer the constraint list option.
I do not, in fact, prefer the constraint list, but I think between the two programming paradigms of this is written declaratively, which I think is the most straightforward way for people to understand what's going on. But what you're describing is what I call the functional programming way of doing it, or the imperative programming way of doing it. And that is the way I prefer, because I guess I think of myself as having come from software engineering first and then operations research second. It also, the functional way of doing it also aligns strongly with my view of, just abstract math and how you define things in math notation. Functionally, there are very few differences. If I had had more time, and maybe this is something we can revisit in a future session, yeah, I actually describe that in a lot of detail here, right? Using a rule, what is this equivalent to? Why would you use a rule instead of an expression? This would probably take me another 20 minutes to go through, but that's one of the things I wanted to highlight in the fourth example.
Yeah, and I guess just to quickly mention to everyone in this, I know you've made this repo public, and we can repost the link to the repository if you want to be able to refer to any of these examples.
You're more than welcome. And in fact, if any of you wants to contribute to this repository, add your own examples, fix the mistakes I've made, feel free. I will see your pull requests if you open them. And do feel free to share.
Sounds great. It looks like Connor has his hands up.
Go ahead.
We talked about this before, but I think it's like useful to know about. But like, how does Pyomo like handle sensitivity analysis?
So I would not say, well, I think to answer that question, you first need to understand that Pyomo can only do what the solver lets it do. Right? Pyomo cannot or does not add functionality beyond what each of the separate solvers that it supports can do. So certain solvers, like especially the commercial solvers like Cplex and Gurobi, absolutely support sensitivity analysis, getting the reduced costs, getting the shadow prices of a solved model. And there are interfaces in Pyomo for extracting, or I should say first, setting up the model to grab those values when you solve it, and then accessing those values after you've solved it. But you can only do that with certain solvers. In Gurobi Py, that should be built in. Because Gurobi definitely supports it. So I don't know exactly how to do that in Gurobi, but I'm almost certain that you can get that information using Gurobi Py. Yeah, maybe I should add an example in this repository for how to do that with Pyomo.
I had a question. I know we've talked about this before, but I was wondering if you have, if you wanted to share with other people, when you look at Pyomo, you often run into this idea of an abstract model. And like, what's the value of the abstract model versus the concrete model? And when should you use which?
So, right, let's go to the place in the code where I've defined this. What we're talking about right now is this line of code. When we initialize the model, when we construct the model, we're using a concrete model constructor. This is in contrast to using a abstract model constructor. Insofar as defining the constraints, the variables, the constraints, and the objective are concerned, there are no significant differences. The reason you'd want to use an abstract model is if you want to delay, or I should say postpone, actually defining what the parameters are, or the sets. I've personally never had a reason to use the abstract model. I have a hard time thinking about the use cases for that. So I would say, 100% of the models I've ever developed were developed using concrete model, and I don't have a whole lot of expertise on the abstract model or the motivations to use that. But the main reason is that you don't want to define all of the parameters up front. Like we have these dictionaries and we pass them into the model. You can build the whole model without doing that, and then basically plug in the parameters after.
Yeah, it's interesting because like when you look through the Pyomo documentation, I feel like it's kind of strongly skewed towards the abstract model. And I was wondering if like maybe that's more similar to the way some other, like if they're mimicking, like, I don't know how GAMS does it, but like it's some other software, how they like to set up their models. And if it's like one is designed to mimic one way and one is designed to mimic the other way, but I don't know. I've always kind of, to me, the concrete model is more intuitive, and that's what I use too.
I was just thinking too, back to your other question about using expressions versus rules. And maybe something I should say, I don't have to go through this whole example, but one reason you'd want to use a rule and the capital C constraint constructor with a rule as opposed to constraint list with expressions is that after you've completed constructing that set of constraints, you can access the constraints by the indices in which they're indexed. Whereas with the constraint, it's just a flat list. Even if the constraint is indexed in 1, 2, 3, 4 different index sets, the constraint list itself is just one-dimensional. So you access it with the index 0 to whatever the length of the list is. But if you had a constraint that was indexed in I and J, then you could say model.constraint brackets I comma j and get the constraint back out of that, which may be useful for if you want to debug or get the slack of an inequality constraint after you've solved it. I don't know. There are good reasons to use a rule other than the difference between declarative and imperative programming.
Well, great. Does anybody else have any questions? All right. Well, this has really been amazing, Brent. Thank you so much for putting this together. And yeah, so obviously we've been recording, so I'll follow up with the recording link, which I think we're going to put on YouTube, and the link to the repo as well. So yeah, thank you so much for putting this together, and it's been super, super helpful.
I just want to follow up that if anyone has questions, I know I didn't cover installation hardly at all, but if anyone has questions or issues installing these things or solvers, you can shoot me a message on Slack or send me an email, and I'll try to respond quickly to those.
Yeah, I will say, I think Milad had asked about installing IPOpt in the research Slack channel. So great place for asking installation or specific questions like that. So feel free to use it. All right. Well, thanks everyone. And I guess tomorrow we have our happy hour, so you should come to that.
All right. Thanks everyone. Have a great day.